Okay, until the year 2000 then, I'd been just working on computer in CAD, mostly on virtual designs. I had actually begun a prototype of a D50, but really it was mostly all on screen. In the meantime, after quitting B&W, Robert had gone to live in South Africa because most of the musicians on his new record label, which was now Melt 2000, were South African, and it was only natural. One day I got a call from Robert saying, I've been talking to a couple of guys. One of them, Philip Guttentag, is the ex-South African B&W distributor. And his friend, Bruce, has a dealership where he sells B&W. So they know B&W really well. In fact, they know you. I didn't know him, but... And they certainly know the Nautilus, and they know your design philosophies. They're thinking of starting a loudspeaker manufacturing company and would be very interested to meet you, and maybe you can do some consultancy or something. I thought, well, why not? I mean, I wasn't really doing anything better. So I went down to Durban, where Philip and Bruce were living, and this guy had an amazing studio with loads of equipment and a pair of Nautilus, and I really took this thing seriously. And we got on, we just got on, and it was very, very quickly obvious that I could work with these guys. And by then, also, I'd got the pro thing out of my system, and I was actually doing some consultancy for another pro sound company in the UK. And so the time had come where I could actually turn back to domestic audio, and it was getting interesting again. So you've already seen where I was coming from with the Micronaut, the little sphere, but that was a fully active design. And very early on, Philip and Bruce both said, no. We're making a funny-shaped loudspeaker. It's going to be difficult enough to sell this thing without it being active only. You have to design passive filters, otherwise it's a non-starter. I'll come back to the details of passive versus active later, but yet again, computer software came to the rescue, because at this point, a company called Linear X had come up with some software called Leap, which is a network analysis program specifically designed for loudspeaker crossover analysis, and it had an optimization function. And again, I'll show you later, but this made all the difference. Anyway, so I had the D50 and the D26 designs pretty much complete, but the base unit, well, I had this crazy idea that I was going to do without chassis. I was going to mount the magnet. Well, if you think back to the cross-section through the sphere, it had the cylinder in the middle. The magnets were going to be mounted directly onto that, and the cone would be mounted directly to the edge of the cabinet, and so I didn't have a chassis. Again, pragmatically, Bruce and Philip said, look, making a speaker without a chassis is actually going to be really, really hard work. It's much easier if we can have a unit that you can build and test and put into a box. So, of course, then I had to actually develop a loudspeaker chassis, but following the simple rules that were by then really crystallising of having a minimum of obstruction behind the cone, it became pretty obvious that our chassis would have these very thin struts. It's very open. It's about 90% open. The struts are quite deep in that direction, but in the direction against the airflow, they're very, very thin, so the air can pass easily without resonances or inflections as ever. The thing about bass units is they have to move. They have to move quite a long way in some cases. And when you look at this detail of the construction, you have the dome here, and you have a volume of air, and the pole piece of the magnet, if it's solid, acts like a piston in a cylinder. And it prevents the motion of the cone. So at low frequencies, where the thing wants to move a long way, that damping effect really restricts the motion. Of course, there's a simple solution. You can just drill a hole through the magnet. No problem. Now you've got your excursion back. The thing can move quite freely at low frequencies. But the problem is, as ever, when you combine a volume of air with a hole, it resonates. I can show you that very clearly in this frequency response. You can see that resonance, and it's at a really annoying frequency, because this driver is supposed to be a low-mid driver, going up to 800 hertz. This is at 350 hertz, right in the middle of the band. It couldn't really be in a worse place. But the interesting thing is that It's not something we'd ever noticed before. It's not something I've ever noticed anyone else make a comment on before. But once you've homed in on it, it's actually quite obvious. And you can hear it. If you put pink noise through the driver and you just block and open the hole with your finger, you can hear the frequency of this thing moving around. Thankfully, there's an easy solution. If you perforate the former, the resonance, which starts off quite sharp in Q and in the middle of the frequency band, gradually goes up in frequency and down in amplitude until it's just out of the picture. So again, if I just show you that. So 50% perforated former completely gets rid of that problem. Okay, Newton's third law of motion. Every action has an equal and opposite reaction. Well, what on earth is the relevance to loudspeakers? The force that acts on the voice coil, which pushes the dome or diaphragm forward, acts equally and in opposite direction on the magnet. But of course, the magnet is 100 times heavier than the dome. So the amplitude of vibration is 100 times less. Not only that, but the actual amount of exposed area of the magnet is also much smaller than the dome. So one way or another, really, the sound coming from the magnet in its own right is insignificant. Well, here's a little example of something which is, pretty much a solid piece of metal. You can probably just about hear it. It's actually not a dissimilar example to the vibration in that magnet. It's a piece of metal with small amplitude vibrations, which in themselves are fairly inaudible, until I attach it to a cabinet. But there is a very, very simple solution. A little piece of silicone O-ring, just put between the metal and the cabinet, completely isolates one from the other. And so in our mid-range units and our tweeters, we have little rings of silicone between the magnet and all the supposedly stationary parts. So one between the cabinet and the magnet, and a couple here between the horn and the magnet. You have to have two to stop the thing flopping around. Great. For mid and high frequency, it is a very total and effective solution. The problem comes with bass units because typically a bass unit's got this heavy bit on the back, the magnet, and you're trying to attach it at the front. And you're trying to attach it on a load of rubber, on a load of soft rubber. So inevitably the speaker just wants to do that. The simple and complete solution, well, actually just a minute, let me just illustrate what happens if you have a pair of drivers mounted on the front of the loudspeaker cabinet. Now I'm going to use these drivers to illustrate the mass of the cones, and I'm going to be the magnet and the cabinet. So as I move the two things in and out, you can see it shakes me about good and proper. And that's the normal situation with front-firing drivers. But the solution, the very simple and complete solution, is you just do that. Now my body is completely stationary, forces balance out. And in nearly all the Vivid loudspeakers, what we do is we couple a pair of bass drivers together with a dual-threaded tensioner on either side of the cabinet, and it completely removes the reaction force from the couple, and so the transmission of vibration from the chassis to the cabinet is eliminated. It is, again, a very total solution. There is another aspect to reaction cancelling, which I'll come to later, and that's the no need for a heavy enclosure, but I will come back to that in more detail just a little bit further down. As far as this part of the presentation is concerned, it's about removing transmitted vibration from the shell. Right. So we have these nice smooth enclosures giving us nice broad nice broad dispersion. Have well-behaved domes. We have nearly ideal rear enclosures, all working together to give us exemplary individual driver performance. So can we just connect them all in parallel and stick them on amplifier? Of course not. We put low frequencies through a tweeter, the thing will try and move so far it will break. We put high frequencies through a bass unit and you'll excite resonances and breakups which will sound absolutely horrible. So we have to divide up the frequency spectrum and deliver the appropriate bands to each driver, and for that we need a crossover. This is a simplified illustration of a gear crossover. You've got crossover points of 220, 880 and 3.5 kilohertz. Well, that's the beginning of the problem, but actually just the frequencies is just part of the problem. What about the shape and the slope and all that sort of thing? There is actually an infinity of different styles and slopes to the crossover. But we, fairly early on, decided on a category called Linkwitz-Riley. Just briefly, the thing about Linkwitz-Riley is that through crossover, the drivers remain in phase, and that just simply means that they move together. The nice thing about drivers that stay in phase is that the at crossover itself, you get a lobe and it's on axis. If you use an odd order crossover, now these things are quite popular at the moment. Conceptually it's nice, just one big fat Mundorf capacitor between the amplifier and the crossover seems elegant. If you're worried about having components in the signal path, it certainly seems to make sense. But the problem with odd order crossovers is you get off-axis lobes at crossover. And that means, of course, that you've got a bit of a reduction in output on axis. You can compensate for it. You can put a little lump in the crossover to make it flat. But the trouble is that now you've got this beam pointing at the floor, at the ceiling, which actually has more energy in it. And so you'll get that reflection with more energy in it, arriving a tiny fraction of a second later. And that actually, ultimately, is a pretty uncomfortable, non-ideal situation. So we're firmly committed to Linkwitz-Riley fourth order filters at the moment. And it's really important that you do them accurately. Okay? So going back now to passive crossover design. So as I said, until my Vivid Audio days, I always thought that it was only possible to do accurate filters with active electronics. But now we have this optimization tool. Now, I have to remind you that before then, when you did a passive crossover, it was a bit Heath Robinson. You knew roughly where the components were going to be, and you knew roughly what the value of the components should be. But when it came down to actually making it fit the curve, you ended up doing a lot of trial and error. And we used to, at BMW, have two big boxes of capacitors and inductors, and you'd start the thing and you'd see that it was a little lump here and a bit of a trough there, so you'd change that inductor for another one. Did it make the lump worse or better? And if it made it worse, then you'd go the other way, and if it made it better, you'd carry on going and you would just go round and round the loop. Very Heath Robinson, very trial and error, and also you'd end up with quite horrible impedance curves sometimes, but anyway. Now we have this network analysis thing. It does exactly the same job, really, as trying random components, but it does it very, very quickly. It's still trial and error. It's still a dumb program. It just tries to make the curve fit as accurately as possible. We start off here with the raw D50 frequency response, and then in red you have the target response. So as I say, you have to know roughly what you're doing. So you build up a filter on the in software, and then you just press this wonderful optimize button, and off it goes, and picks and chooses and changes all the components. It just goes round and round the loop, trying to make it better. And it's incredibly effective. This is the actual result that you get from running an optimizer. It can be within a fraction of a decibel from your target function, which is, I could never have dreamt of such accuracy. This is the same thing with C125, so you can see there's a raw driver, there's the target, there's the initial performance, and then we just press the optimize button. 30 seconds later you have this wonderful match. But the real proof that the thing is working is when you put the two drivers together, and you can see how very perfectly they sum. And that's the whole point. If you're going to make Linkwitz-Riley filters, they have to be done accurately, otherwise they won't sum. Now, the result isn't simple at all. Of course, if you're one of those people that likes the idea of a simple first order crossover and you see this thing, it's probably the complete anathema, because we we don't shy away from complexity. If that's what it needs, that's what it gets. The other thing about complex four-way crossovers is that you have to have accurate components. But again, it's not something we're worried about. We make our own inductors, so we can wind them to within a fraction of a percent of the required value, and we get some high-quality polypropylene inductors. And the result is actually very, very close to the required value and very repeatable. All air-cored inductors, of course. We wouldn't put an iron core in the signal path. And we always use polypropylene for the main signal path capacitors. These electrolytics are just an impedance linearizer, and they don't actually come into the signal. There's one little thing about our crossover construction. Way back at the beginning of the B1 development, we worked out what the crossover was going to be, and naturally enough, I just sent the design to one of the big OEM suppliers in Taiwan, a company called Elitone, who supply, at the time it must have been like 80% of the world's loudspeaker manufacturers. We got a beautifully presented, professional-looking crossover back and put it in the B1 prototypes and listened to it and thought, oh, no, hang on, they made a mistake. There's something wrong with this. So I measured all the components. No, it didn't seem that there was a problem. So then we got the prototype wooden crossover board and gradually moved the components from the printed circuit board to the wooden hand-wired board. And bit by bit, it started to make sense. None of the components were wrong. And when we finally migrated all the components from the printed circuit board to the piece of wood, it was still sounding wonderful. All the components on a piece of wood sounded much better than on a printed circuit board. It turns out that actually, and this is where, as an engineer, it's very frustrating because I can't give you an explanation, but printed circuit boards don't seem to work in loudspeakers. I might be an engineer, but I'm also quite pragmatic. Since we have a perfectly effective and simple solution, you hardwire the crossover and it sounds wonderful and transparent. That's the way we do it. It's a little bit more labour intensive, of course, but it's a small price to pay for the improvement in quality that we get. So the result of all of that was that in 2004 we had the B1 and the derivative K1 and C1 products when we went to market. So those oval loudspeakers incorporating everything I've mentioned so far, the smooth shape, the optimized domes, the tapered tubes, reaction cancelling, and the optimized crossovers. I'm going to break to listen to a little more music, and then we'll go on to what happened when we moved from the oval series to the gear series. Lots of new tech, lots of new IP, but there was one thing which was actually pretty ordinary from an acoustic point of view, and that was the bass chain. It might be a nice quirky shape, but actually from an acoustic point of view it is just still a void with two holes. Actually the elliptical shape does help a little bit because of course we put stuffing inside the box to try and absorb those top to bottom parasitic vibrations. But fundamentally it's the same old story. So let's have a look at another little computer model. This is a plain reflex box. You've got the chamber there with a port, and the port output is this faint curve here, which adds together with the driver output to give this lovely, well-behaved, high-pass bass response. Great. But what about these horrors? Well, these are the eigentones formed by the wave bouncing between the front and back of the cabinet. Well, okay, that's a computer model.
Hey.
Sorry, no.
No, it's all right.
Yeah, you continue.
Well, I'm just making sure that you're not going to...
No, I'm not going to blast you away.
Okay, so those are the eigentones. This is a computer model, all very well and good. Is it actually as bad in reality? So here we've got a real box, nice little wooden box, it's bass reflex, you can see the tube there, and this is the actual microphone output from that combination. You can see, yes, actually, reality is every bit as bad as the computer model predicted. And we've got the added advantage here in this waterfall plot of being able to see not only the resonances in the continuous frequency response, but you can see how long they ring. These are very audible resonant phenomena. Well, okay, we know that an exponential horn absorbs tube resonances really effectively. Would it work with a bass reflex? So this is a typical Nautilus style exponential horn where the diameter of the horn at the mouth is the same as the driver, and then it tapers off. And the volume of this horn in this model has been calculated to be the same as the volume of the chamber that you saw before. So if it were just a volume of air, the resonant frequency would be the same. So there's the port, but we see that actually the port output has hardly any resonant quality whatsoever. And indeed, when you add it to the signal from the front of the driver, the overall shape is very, very poor. Remembering that before it was up here, you've lost more than 10 dB of output. Actually, the port is counterproductive in that case. But let's not forget that up there in the upper frequencies, indeed, it is completely free of eigentones or resonances. So was there a combination of a bass reflex and some sort of exponential horn which would give us the best of both worlds? Well, it turns out that yes, indeed, there is. If you get an exponential horn where the cutoff frequency is about 4 or 5 times the port tuning frequency, then it doesn't take away the energy of the port. You can see here that the filter curve is as it was before, but you do get the absorption of the eigentone. So we have actually got the best of both worlds. Does it work in practice? Here's that self-same wooden box, and that was the response we got with the plain box. And now I've just plonked it on. It's almost a question of any old horn that was lying around. It happens to be the absorber horn from a C125 in a G1, but you can see I haven't taken much care to make sure that the horn is the same size as the box, and it even still has the step from the gear application. But you can see how completely effective it is in absorbing those resonant spikes. So yet again, we've got a very tolerant technology, a very easy to apply technology, which is really, really effective. So that's another 3D representation of what we need: a chamber, a port, and an absorber. So I knew what we wanted. I knew the sizes involved. This whole thing is just a page from my computer doodlings. You can see the necessary shape, or the area law, as it's called, in these little curves. And it was just a question of how are we actually going to package this thing into an actual 3-dimensional loudspeaker. I had a bit of an obsession with symmetry, as you can see. So these three are actually, as you see, they became the first idea, but that's the view from the side and that's the view from the front. So, in SolidWorks I came up with this creation. It's about this tall. These are 15s. So this Dapolito's with a pair of 125 D50. It's a monster. It's a Leviathan, really. And when we showed it to a friend of ours, a chap called George Elphick, he just burst out laughing and said, "There is no way. This is not a domestically acceptable product. So you're never going to get any of these into people's homes." I still believe that we'd sell 1 or 2 if we did it. But anyway, we listened to him. The guy has some experience in the field. And he said, "Is it actually necessary to have that other spiral at the bottom?" I thought, well, no, you're right, actually. It is my obsession with symmetry. Let's just cut it off and see where we go from there. So you can see his paper doodlings there where he's cut that bottom off. And that really was the beginning of that new direction. Needed a little bit more work because actually the correct spiral, that is to say the spiral that follows the area law that the maths required, is actually a little bit diminutive, and it really didn't balance visually. And I think it's reasonably important that we get these things right. So another friend of mine, Chris Stevens, he's an artist, a painter, and we just went to the pub with a pad of paper and a pencil, and he started sketching these things out. And he just suddenly said, "Why don't you just put a hole in the top to make the thing visually bigger?" And of course, that's exactly what we did. It expands the size of the spiral, and the eye sees it as a better balance. But also, at the same time, Chris just casually threw in that little S-shaped crease. He didn't even mention it at the time, but it turned out that was to become another important aesthetic feature of the gear design. See, although I'm fundamentally an engineer, I think it is very important that we allow design to creep in whenever possible. I may not, I admit that not everybody agrees with our design statements, but we have fun doing it. Anyway, so the next bit was really all about plasticine modelling. Again, I enjoyed myself greatly with lumps of plasticine. The kids joined in, it was great. We ended up with a whole row of little models, and eventually chose this one as being a good balance of height and the size of the spiral and all the rest of it. And from this model, I extracted these line drawings and then put it into the computer and ended up with a nice three-dimensional computer model. And then I started to think about the size of it, and about the wall thickness, and about the material that we were using at the time in the ovals loudspeakers, which is a polymer concrete, as we call it. It's polyester resin and ground up rock with a little bit of carbon fibre to give it some extra strength. It's quite dense. It's density of about 2.5 or something like that. And I started to think about what the weight of this thing was going to be. It's like, it's going to be 250 kilos if I'm not careful. Oh my God, no, this is all wrong. I know that there are other loudspeaker manufacturers who are not shy of a bit of weight. They tend to be from the other side of the Atlantic. But I honestly didn't want to go that way. I think it's actually, in this day and age, we should use engineering to reduce weight wherever possible, and to reduce the consumption of materials wherever possible. Now let's go back to that little thing about reaction cancelling. The line I had highlighted then. No need for a heavy enclosure. When you have forward-firing bass drivers, quite literally, especially if they're heavy cones, which some people use, the cabinet jumps around in reaction. With reaction cancelling, not only do you not get the transmission of vibration, but the cabinet stays still. So we no longer need what some people call seismic mass. But you still need a cabinet to be stiff because it has to hold the sound in. So now the requirements are for a light, stiff enclosure. Well, light, stiff materials are actually the mainstay of all those people building aerospace, satellites, racing cars, high-performance yachts. All of those guys want light, stiff materials. And they all end up with the same sort of solution. And that's basically what's known as a stressed skin composite sandwich. So I've got some little bits and bobs here to try and help demonstrate. I've actually got two different demos. The first, I've got two bits of foam rubber here, stuck together, and you can see it's pretty floppy. And this is an aluminium honeycomb, also pretty damn floppy. It's very, very light, certainly a lot lighter than the foam rubber. And the amusing thing is when we stick these things together, we end up with something which is a lot stiffer than just the rubber on its own, but it's almost the same weight. Really, we've vastly increased the stiffness with a very marginal increase in weight. This little table here shows some figures with just the two things stuck together. We have this nominal stiffness called unity. If we increase the thickness by a factor of 4, the stiffness goes up by a factor of 48. So it's hugely beneficial to space your skins apart. I have another demo here which unfortunately is a little bit difficult to hear, but this is perhaps more relevant because it's all about the resonant modes, the structural resonant modes in the shell. It's the fundamental you're trying to hear here. It's about 150 hertz. If you want to come and try this yourselves later, or you can pass it around, about 150 hertz. But then we just stick two pieces of really thin, ordinary aluminium foil onto the outside. And the result is 750 hertz. We've gone from 150 to 750 hertz. An incredible change. And again, the core is so light. So I knew then that the G1 was going to be made using stressed skin composite. and we then just needed to learn how to do it, because at the time we were used to just mixing stuff in a pot and pouring it into a double-sided mould, and this was a whole new ball game. As I said, vacuum infusion is a technique that's used by boat builders. So I just Googled high-performance boats Durban vacuum infusion or something like that, and it came back with the name of a company, and they turned out to be literally 5 minutes from our front door. And indeed, they make, there's an inflatable dinghy for illustration, but they make really high-performance racing catamarans using the vacuum infusion process. So very generously, they said, we can't make shells for you, we just don't have the capacity, but we'll show you how to do it, which of course is actually exactly what we want. We like to do things ourselves. It's much more satisfying than handing it out to other people. So this is the basic tool. It's a single-sided glass fibre tool. You lay the layer of glass fibre in the tool. Then we use balsa for the lightweight core. These little pieces of balsa, it comes in little squares about that sort of size. And the chaps who build these things just put a little squirt of glue, stick the balsa in, and they gradually build up the whole layer of balsa wood. They then actually cut little triangles to put in the spaces as well, so it's quite labour intensive. And then you put another layer of glass fibre on the top of that. And then you wrap the whole thing in a flexible polythene sheet, seal the edges with this black tape. Around there you can see the perforated tube that will feed the resin in, and these two pipes in the middle are connected to a vacuum pump. You turn the vacuum pump on, the whole thing just gets compressed by the air pressure, which is brilliant, because the thing is about fibre reinforced plastics is that you don't actually want plastic, you want fibre, and you really want the tiniest amount of resin to just hold it all together. The resin is just the glue. It actually imparts no structural benefit itself, it just adds weight actually. So we're trying to keep the resin fraction as low as possible, and the vacuum infusion does that job magnificently. So you pull the vacuum, get everything nice and tight, and then you open the valve and the resin shoots in and gradually diffuses through the whole thing. The result is that each half of a G1 cabinet now weighs just 12 kilos. So a huge improvement in total weight. The finished product isn't just 24 kilos plus a little bit. It's a lot heavier, but that's because the drivers and the crossover and some of the reinforcing components all add tremendously to the weight. In the past, people have said, glass fibre? Why do you use carbon fibre? Surely this is a high-performance product. Well, we could use carbon fibre, but you can always get the same resonant modal frequencies with glass if you just use more of it. And all that changes is that the total weight, of course, goes up. Now, I've said that we want the thing light, but I'm not obsessive about it. If we were sending the speakers into space, then we'd use carbon fibre. But as long as these are terrestrial loudspeakers, we'll stick to the glass. The G1 was to be a four-way loudspeaker, whereas everything we've done so far was what's known as a 3.5. So if you think of a B1, you've got drivers on the front and the back. They both work together at low frequencies, but as you go up the frequency spectrum, you're left with just the front one working up to the mid crossover point. With G1, right from the beginning, I was pretty sure that I wanted to be a proper four-way system. That's great because it meant that the bass units could be just proper bass units. They could move a long way, and they didn't have to also produce mid-range. So they could be optimized for the bass. When I started to look at the actual magnet construction for an optimized bass driver, I could see that the topology that we used in the C125 in the B1 wasn't really optimal for a bass-only magnet. The magnet in the C125 is here, behind the voice coil. What I realised was that if you move the magnet round to the side, you make much better use of the magnetic material. And I can show you, again, in a computer FEA model, the actual analysis results here. This is the C125 model, where the magnet is here at the back. I'm sorry for the changing colours, it's confusing, but they are actually all the same things. So we go from this bit, the very same volume of magnetic material applied to the side of the voice coil there, and you can see these are flux density plots taken in a slice along the magnetic gap. So this is the original C125, and it's about 12 millimetres long, is it? No, 18 millimetres long. And this is the topology that's then used in the gear driver. So you can see it's almost double the length of usable flux. And also there's another little detail. If you look, the C125 has a bit of a slope on it because it's a longer path length around the outside, whereas that slope goes away completely in the gear approach. So really a significant improvement. I didn't realise quite how important that improvement was. It's not just that you get a longer linear throw and all those lovely things and use less magnet, which is obviously great for the cost and everything, but there are actually some other subtle improvements further up the frequency range which aren't that important in a gear because they are bass only. We used the same change when we went to the B1 Decade, and if you've heard the difference between B1 Decade and the traditional B1, an awful lot of that difference is because we've moved the magnet from being behind to being adjacent to the voice coil, but that's for another day. So there we were, 2008, we launched the G1 at CES, and I suppose you could say the rest is history. In resume, our products, the gear in particular, all have this smooth exterior shape to give the nice broad horizontal dispersion. We use tapered tube absorbers both behind all the drivers, mid and high, but also now we have a technique for using the very same technology on the bass reflex. Everything is decoupled or reaction cancelling to prevent vibration transmission and also to allow us to use lightweight sandwich composites. We use optimized passive crossovers. Anyone interested in talking to me about the pros and cons of going active, you're very welcome to come and hassle me afterwards. And finally, we have our own spray booth. And the great thing about having your own spray booth is you can do all sorts of interesting finishes. And Mr. Lecaque has exploited that facility to the max, and he has really given us some challenging finishes, but we're really happy with the results that we're getting because really it's the icing on the cake. We can really do some great finishes, and Ewout has also been very, very instrumental in introducing matte finishes. And matte finish it's an incredible thing, but it isn't just a change to the finish. Really, it changes your perception of the shape, which is a really interesting new direction. Anyway, so there we go. I hope you're somewhat the wiser. I hope you have a little better understanding of why we have such odd shapes to our loudspeakers, but please do come and talk to me, and if you have any further questions, I'd be more than happy to ask. Help even. Okay, cheers.